Okay, so we had left off at this problem at the bottom of the page. And just to refresh your memory, the first thing that we needed to do was find the mole fraction of hydrogen gas and of helium gas. So we were given grams of both hydrogen and helium, so we needed to convert into moles of each. And so when we did that, you should have gotten approximately 0.5 moles of hydrogen gas and 0.250 moles of helium gas. And then you just divide each by the total number of moles, which is the two of those added together, which is 0.750. And then divide the part over the whole to find the mole fraction for each. Okay, so your mole fraction for H2 should be 0.667, and chi is the symbol that we use for mole fraction. Okay, and then your mole fraction for helium should be 0.333. Okay, we don't need units on those. The next thing that you'll do, so the next part does not involve the mole fractions, but what you'll do is you'll use the moles that you found for each gas individually. So the moles for H2 and the moles for helium, and then plug each of those into the PV equals nRT equation. Okay, to find pressure for each of them. Okay, and so when you do that, your pressure for H2 should be 12.3 atmospheres, and then your pressure for H2 should be 6.15 atmospheres. Okay, and then you can obviously just add those together to find the total pressure, which should be 18.45 atmospheres. Okay, so a few steps involved there, but nothing really different than what we've been doing. Okay, so the next thing we're going to talk about is the effusion and diffusion of gases. And for all intents and purposes, we can think of these as being similar when we're doing mathematical relationships for these, but the difference is that diffusion refers to the mixing of gases. So when we talk about the rate of diffusion, what we mean is how quickly particular gases are mixing together. Okay, and then when we are talking about effusion, we mean how a gas is moving through a tiny hole. So this image here is meant to represent that. So if you have a gas and each of these represent particles, and then the gas is going through a hole into a vacuum, when we talk about the rate of effusion, that's what we mean. So how quickly a gas is able to pass through a pinhole into an evacuated chamber. Okay, so both the rates of diffusion and effusion are inversely proportional to the square root of the mass of its particles. And so this alpha means is proportional to. And so what this ends up meaning for us in terms of math is that the greater the molar mass of the gas, the slower the rates of effusion or diffusion. Okay, and that should be obvious based on these relationships here. So the larger your denominator, the smaller each of these rates is going to be. So each of these equations at the bottom are related to kinetic energy, and we can think about the kinetic energy of our gas particles. So kinetic energy equals 1/2 mv squared, where m is mass and v is velocity, and then also kinetic energy equals 3/2 RT, where R is the gas constant and T is temperature. Okay, so if you scroll down to the next page, if you set those two equations that we just talked about equal to one another, this is what you should get, okay? And then if we isolate the velocity, this is the related equation, and this is sort of the equation that we're most concerned about using in terms of gases for the AP, okay? And So this equation really doesn't come up all that much, but if it did, you would know what the constants or what the variables represented. And what this means is the root mean square velocity. Okay. So it's more relevant when we get down here to talking about the relative rates of diffusion and effusion for particular gases. So don't worry too much about this particular equation. It really should not come up very much, if at all. Okay, so when we look down here, this is really the equation that we're most interested in. So remember that when we were talking about the rates of effusion and diffusion, we were only setting them proportional to the inverse of the square root of the molar mass. And what that means is that we aren't actually going to be solving for the precise rates of effusion or diffusion for particular gases. So what we'll be doing instead is comparing the rate of diffusion or effusion for one gas versus another. So the relative rates of diffusion and effusion of two gases at the same temperature and pressure are given by the inverse ratio of the square roots of the masses of the gas particles. So this is essentially combining the proportionality equations that we were talking about earlier. So what this means is the rate of diffusion for gas 1 in the numerator here, okay, divided by the diffusion for gas 2, okay, is equal to the square root of the molar mass of gas 2 divided by the square root of the molar mass of gas 1. So you want to make sure that you have these relationships correct, where gas 1 is in the numerator for one rate, and then if that's the case, then it should be in the denominator when you're talking about the molar mass, and vice versa for gas 2. So they need to be diagonal from each other when you're setting up this equation, because remember it's the inverse of for the proportion. Okay, so if you scroll down to this problem, it reads, ammonia has a molar mass of 17 grams per mole. Hydrogen chloride has a molar mass of 36.5 grams per mole. What is the ratio of their diffusion rates? Okay, so let's do this one together. So I know that I can choose whichever one I want to be gas 1 or gas 2. So let's just say that NH3 is gas 1. Okay, and HCl is gas 2. Okay, so that means that the rate of diffusion of NH3 divided by the rate of diffusion for HCl should be equal to the square root. So I need the rate of HCl. Since that's down here, then I need the molar mass of HCl in the numerator here. So it should be 36.5 grams per mole, and then divided by 17.0 grams per mole. Okay, and so when I divide these two numbers, this is the only thing that I have to plug into my calculator. I should get the ratio being 1.47. So what that tells me is that NH3, which is in the numerator, has a rate that is 1.47 times faster relative to HCl. Okay, so when you get down to the next page, there are a couple of problems that you need to work. The first one is essentially identical to the one that we just did. So take a moment and pause the screencast and work that problem. Okay, so what you should find is that the effusion rate of hydrogen should be 13.2 times that of uranium hexafluoride. Okay, So scroll down to the next problem, and here you set it up the same way, except what you're solving for this time is the molar mass of some unknown gas. So you are given the rates of diffusion for each gas individually, and so you can plug those into the rate positions of your equation, and then you're solving for the molar mass. You'll want to be careful how you do that math. Make sure you're getting rid of the square root. Okay, so take a moment and pause the screencast and solve that problem. Okay, so when you do that, you should find that the molar mass of the unknown gas is 64 grams per mole. Okay, so scroll down. The last thing we're going to talk about is real gases. So remember that this is some of what we've already discussed. The ideal gas equation is a model only for real gases. So no gas is exactly ideal, okay? And we said that gases come close to being ideal gases under conditions of low pressure and high temperature, okay? Under certain circumstances, the difference between a real gas and an ideal gas becomes significant. So in other words, the ideal gas law is not an appropriate way to be predicting the properties of gases, okay? And those are under conditions of high pressure and low temperature, okay? So remember, some of our assumptions of the kinetic molecular theory was that gas particles don't take up any volume, and also that gases exhibit no intermolecular forces between their particles. So under conditions of high pressure, okay, the volume of the gas particles becomes significant because there is less empty space between the particles. So what they mean by high pressure is also low volume. So in other words, as the volume of your container diminishes, when you're thinking about the volume that the particles take up relative to that, suddenly the gas particles have an appreciable volume relative to the container that they're in, okay? And then at low temperatures, the particles are moving a lot more slowly, and so they're a lot more likely to be able to have intermolecular forces. So if you'll scroll down, van der Waals equation is what corrects for these discrepancies that can occur for real gases. So you'll notice that this still has the same appearance of our PV equals nRT equation, but there are these variables which are slightly different. Okay, so the first thing we're going to talk about is pressure. So there are a few things that are going to come into play when we're thinking about the pressure being different for a real gas. And those things that we have to take into account are the attractions, okay, and the strength of those attractions between the particles, and then also particle concentration. Okay. So if gas particles have intermolecular forces between them, that is going to lower the gas pressure, okay? And the amount of attraction between gas particles depends on the concentration of gas particles and the magnitude of IMF. So this m squared over v squared part of our equation corrects for concentration. Okay, and then the A corrects for the attractive forces between particles. Okay, so A is a constant, which is different for different gases, and it takes into account the attractive forces between molecules. So that value of A gets larger when you have stronger attractive forces. So you don't need to know how to implement this equation, you just need to know how to relate it in a conceptual way to gases, okay? So you won't be asked to plug in particular numbers, most likely. And then Okay, I will explain the rest of this part of the equation in class, and we'll go over these in-class problems in class since we're running out of time. Okay?